Assalamu alaikum and welcome to today's session. So in the last class, we were discussing about the effect of the variation of exciter gain or the voltage regulator gain, this Ka value on the system stability. So this was the topic that we ended with. So today what we will do, we'll look at some of the simulation and the corresponding eigenvalues before we switch to the new topic. So this was the model, basically, the linearized model for the exciter or the fast acting voltage regulator, where the exciter is actually not modeled in detail because of its fast action. So there is no time constant associated with the exciter, because in the static voltage, static excitation system, we don't have the presence of the rotating machineries. So that's why we don't model it explicitly with the help of the time constants and gains. Rather, we only have the presence of the voltage regulator in the form of the amplifier. So this was the model continued, where we actually replaced the terminal voltage deviation delta VT. So the terminal voltage was represented in the form of the deviation in delta and deviation in EQ dash with the help of two more K constants, that is K5 and K6. And then we had this equation while we replaced this delta VT term. And finally, we came up with the fourth order model. So this is the summary of the fourth order model, where we have four state equations now. And within this fourth order model, basically we have the third order model for the synchronous generator, which is also known as the flux decay model. So the first three equations, they belong to the synchronous generator. And the fourth one is the first order AVR model, which is basically the representation of the simplified IEEE ST1A excitation system. So in here, we have four state variables, and beside those, so these are the state variables: del delta, del omega, del EQ dash, and delta EFD. So because we have four state variables, so that's why it is the name goes with the fourth order model. Besides, we also have two inputs in the form of the mechanical input from the governor side or the turbine side. And also we have the change in the reference set point for the regulator itself, del Vref. And the remaining, all these variables on the right hand side of these equations are mostly K constants. And so you have 6 K constants basically in total. And we have the damping factor, capital D. And also we have some system parameters like the dx is time constant, the inertia constant, and the exciter gain or the voltage regulator gain and time constant. So now some of the values here within in this fourth order model, some of the values would be dependent upon the operating point. That means if we change the operating point, those values would be affected. Like, of course, the K1, K constants. So all these constants, K1 up to K6, would be affected if this operating point is changed. However, there are some other values which are basically the system parameters, like the H value, the D value, the TDO dash value. These are system parameters, okay? So if these are changed, mostly the dynamic of the system would be affected. Also, this K1 to K6, if these constants change, again, the dynamics will be affected. But these are constants, okay? H, D, and TDO dash, these are constants, whereas K1 to K6, these are not constant. These are, although these are known as constants, but these constants are dependent on a specific operating point. So if we fix the operating point, only then this K1 to K6, they become constants. On the other hand, H, D, and TDO dash, like Ka, Ta, all these values, these are constants, irrespective of the operating point. These are constant. These are machine and excited data. They have nothing to do with the variation in the operating point. So once we have this fourth order model ready, we can express those equations now in the matrix form. So now this is again the representation in the form of x dot equals ax plus bu. So the A matrix is the system matrix. The dimension of the A matrix would be 4 by 4. So this is our A matrix. This is x dot ax plus bu. So simply this is a 4 by 4 matrix. So if I want to find out the dynamic response scenario or the stability scenario for this system, simply I have to calculate the eigenvalues. Or another way is simply you make determinant of Si minus A, where the S is the Laplace operator, I is the identity matrix of the dimension of the same dimension as of A. And you equate it to 0, and then you solve for the roots of the polynomial that is resulted in. So you solve for S, and because here you have a fourth order system, so the number of S that you would get would be 4. So you will get 4 roots, and those are simply, we are calling it as the eigenvalues. So now the location of these eigenvalues, or the location of these roots on the S plane, would give us the idea about the stability of the system. So now let's continue with the example that we did in the last class. Basically, these are the same set of data that are used for the simulation of the third order system. So there's nothing new. I've just listed them again. So every time I'm talking about some operating points, so what are actually related, what are the values associated with a certain operating point? So let's see. So to start with, we have an operating point, and it shows us that we have some information about this system. So let's say this is your generator, this is the transformer, and then this is your transmission network. And this is the infinite bus. So this is your VB. You can, if you want, you can omit the transformer for the time being, because ultimately your transformer for this network, your transformer and transmission line both would be series connected. So you can also include this XT within this XL and vice versa, and make it a series, only a series element between this bus and this infinite bus. So this is the generator terminal bus, VT, the low tension side, and this is the high tension side, and this is the transmission line impedance, where we are also saying that we are not considering any of the resistive elements within the armature of the generator for the transformer model and also for the transmission line model. So there are no R elements, no resistive elements are present in the system. So operating point means basically that we are getting some idea about the power flow through the network, how much power is being flown, like the real power and the reactive power, and some information about the voltage magnitudes, and if needed, some angle values. So because we said that the infinite bus would be our reference bus, so without loss of generality, we can consider that this angle would be 0. However, for this network, we are given with VT and PT and QT, these are given. So we can say easily that at this bus, at the generator terminal bus, these values are actually given, PT and QT. And this is the reference bus. So the magnitude of VT is given, but not the angle. So we have already shown earlier that how to proceed with the calculation process for finding out the initial value calculation for the dynamic system. So we have to adopt those steps. So by operating point, basically we mean some information related to the power flow and the voltage magnitudes, and if available, some angle of the voltage phasors. From where would you get that? For a large system, for a practical system, simply for getting the idea of the operating point, you have to adopt the load flow analysis solution. you have to go for the load flow solution or the power flow solution. So the power flow solution would ultimately give you these values: the magnitude of voltages, the angle of the voltage at each of the buses, the power flow, if it is a generator bus, how much power is being injected from the generator to the network. If it is a load bus, how much power is actually consumed by the load at that corresponding bus, and so on. So the operating point information will basically come from the load flow solution. However, for a simple network like this, we can assume that, well, that part is done and we already have the information available, PT, QT, and VT, and we'll assume that this is the starting point of the solution of the system. And then we have some impedance data, like the transformer data or the transmission line data, or you can even, if you want, you can combine both of them, and you can assume that, well, this is the XT, 0.25. Where within XT, you can assume that, let's say this is 0.1 and this is 0.15, something like that. Then we have the internal machine data. This is the generated data. So the Q-axis impedance, the D-axis transient reactance, Q-axis reactance, and the D-axis reactance. These are the values. The system operating frequency simply gives you the idea at how much frequency the power is being generated by the generator. So it's a 50 Hertz system. So that should be Hertz. And all these values over here are actually in per unit. So these are in per unit. I should have mentioned the units, so I will include them. So all these are in per units. This is in Hertz. And this is the base frequency, which is 2 pi into F. And this should be in radians per second. The system damping, it's a constant. So it's a unitless, T equals to 5. You can say per unit. Inertia constant is in seconds. It's in 4. And this is in seconds. The dx is time constant. It's 5 seconds. So with this set of data, we actually simulated the system. So let's see how it responded. So for the simulation of the dynamics, what we did actually, we introduced a change in mechanical input. So that means the system matrix that we have here, simply here in this del PM, the value of del PM, what we did initially from time t equals to 0 to time t equals to 0.1 second, del PM was set to 0. Then if t is greater than 0.1 second, simply we made del PM equals to 0.1. So this is the disturbance that we applied to our system so that we can observe the dynamics of the overall system. And the simulation was done basically with the help of the numerical integration technique, that is the Euler method. So once we did it, then we start from the third order system, because actually we are trying to look at the effect of varying the voltage regulator gain, Ka, on the system stability. So to start with, what we did, I simply simulated the third order system, means we have not included the fourth state variable. Okay, so we have a third order system. So in the third order system, again, we have only these three equations: del delta dot, del omega dot, and del EQ prime dot. So then the corresponding A matrix would be simply 3 by 3. Okay, so this is the A matrix. Then there is X plus, there would be B, and there is U. So because the system A matrix for the third order system is a 3 by 3 matrix, so the corresponding eigenvalues, number of eigenvalues that would be generated, or the roots of the characteristic polynomial, there would be 3 roots. So these are the 3 roots listed over here. And we can clearly see that all these eigenvalues, so there is a complex conjugate pair. So this is a complex conjugate pair. But the real part is negative, and I have a real root, single real root, where again it's negative. So that means all these 3 eigenvalues, they are actually lying on the left of the S plane. So if I denote this S plane by sigma plus j omega, So this is nothing but sigma plus j omega. So sigma is along the real axis and j omega is along the imaginary axis. So these roots would be somewhere, let's say the minus 0.2373 would be somewhere here, and minus 3251, and then plus minus j 6.842. So they would be somewhere there. So because all of these roots are lying on the left of the S-plane, in the left half of the S-plane, so the system is stable. And we can see the response here. So this, for obtaining this response, we, as I said, delta PM is 0.1 when t is greater than 0.1 second. So this was the simulation scenario. So these are the responses for all these three state variables. So we can see that, well, right after the introduction of this delta PM into the system, we have some oscillation, but the oscillation is decaying with respect to time. And the system is settling to a new equilibrium. So it's, as it is settling to some new equilibrium point, so we can clearly tell that, well, the system is stable. So this is the time domain simulation, the time domain response. Del EQ dash, it is the change in the EQ variable itself is some negative value, but again, it is getting settled. And del omega, of course, it is a synchronous machine. So del omega would be ultimately again coming back to 0, because there should not be any del omega. Okay, the system should come back to synchronous speed. But to cater for this del PM, which is positive, your rotor angle would be increased a little bit. So you can see initially it was 0, then the deviation in the rotor angle variable del delta is some positive value. So it is around 0.18 or 0.19, something like that. So your delta, actual delta value would be, of course, delta naught plus del delta. So this is your original value of the delta variable, actual delta rotor angle variable. So if the initial value was probably, I can't remember, probably it was 23 point something degrees. So plus del delta would be 0.19 degree. So then you have to add it, and then you have to get the actual value of delta. Omega would be omega 0 plus del omega, because del omega is 0. So omega would remain at the base speed, which is in per unit, which is 1. Of course, del EQ prime is reduced a little bit. But the response says, the time domain response says that it is stable. So now we move into the fourth order system without changing any of the data that were presented earlier a little while back. What we would do, we would simply introduce a simplified exciter model with a gain Ka and a time constant Ta. And we will keep Ta, the time constant, as a constant. We will not vary it for different cases under consideration, but we will be varying the Ka, or the gain value. So let's start with some low value of gain. So this is the AVR data. So we have Ka equals to 10 and Ta is equals to 0.01 seconds. So this data is actually added with this set of data here. And now with the introduction of the fourth order system, we have these two additional data for the AVR. AVR in short means automatic voltage regulator, the same as the voltage regulator block. So now we, because the system order would be now increased by 1, so we'll have a fourth order model. So there will be 4 eigenvalues. So these are the eigenvalues. Again, we can see that, well, they have all the real parts of the eigen. So we have again complex conjugate, one pair of complex conjugate, and one real. And this is the second real eigenvalue. But all of them, for all of those, we have negative real part. So again, this is stable. So this is from the eigenvalues. We can conclude about the stability. Now we go to the time domain simulation. And we see, well, we have a larger oscillation, of course. The oscillation has increased compared to the previous case. In the previous case, the oscillation was, okay, it was around probably 0.2. However, the duration of the oscillation, it takes longer actually to settle down. Okay, probably the magnitude is almost same. It is 0.2, probably it is around 0.25 or 26, something like that, even much closer to 0.3. In this case, it has crossed the first overshoot, has crossed the 0.3 value for del delta, and also it is taking much longer time to settle down to some equilibrium value, but ultimately it is settling down to the equilibrium. So so it is stable, and again del omega, it has very small oscillation. You see the magnitude is in the order of 10 to the power minus 3. Again, it is settling down to 0. That means there is no del omega in the steady state situation. Del eq dash, now it is going in the positive direction, but again it is getting stabilized, getting settled down, and this is the new state variable, which is delta EFD, and again this is stable because it is settling to some equilibrium value. So now, what's the frequency of this oscillation? Okay, that is important thing, because we call this phenomena as the low frequency oscillation problem. That is coming up in the probably in the last slide of this presentation. So it is called as the low frequency oscillation. So we will also have to look at the frequency at which the oscillations are occurring. So as I said, the frequency would be calculated from the S values or the roots. Okay, these are the roots, and these will actually drive your system dynamics. So what is the frequency here and what is the frequency here? Basically, they have some J0 part. So they are zero frequency elements. So these two roots don't have any frequency term. They have simply magnitude term. Whereas this one, why I'm writing it like this? Because these are nothing but S equals sigma plus minus J omega. So you see, for the real roots, you only have, for the real S values, you only have the sigma, you don't have any omega. So that's why I have written plus J0 plus J0. So there's no frequency associated with that. So the frequency of these oscillations over here, this frequency would be governed by these two roots over here. So this is in omega term, that means it is in radians per second. So if you want the F value, corresponding F for this one, you have to simply divide by twice pi. So you see, twice pi means how much? It is 2 into 3.1416, something like that. You divide 6.844. So how much it comes? Probably around 2 into 3, so it is 6 point something, less than this. So it is probably 1 point something hertz. So you see, the range of frequency that we are now concerned with, it is in the range of 1 hertz. Okay, in the range of 1 hertz. And our power system base frequency is in 50 hertz. So as we said, that our system frequency or the system operating frequency is actually 50 hertz. Okay. So the frequency for our study case, this oscillation case, this stability, small disturbance stability case, we are now concerned with this oscillation over here, and we are seeing whether this oscillation is dying out or not. And that frequency is not actually the 50 hertz frequency. It is not the power frequency. It is rather a very low, very, very low frequency compared to the power frequency. So that's why we call this oscillating frequency as the low frequency oscillation. Okay. But just give me 2 minutes because I have one emergency call to attend. Okay, I'm giving you just pause. Okay, so let's continue. So this is why the frequency under our interest, or for the interested value of frequency, is not actually the power frequency. It is actually 1 hertz. So you have to keep it in mind. And thus this problem that we will see ultimately, that this problem is known as the low frequency oscillation problem. And still now it is not causing problem because the system is still stable. Okay, still now it has not created a problem, but let's see. So what we do next, we would simply increase this Ka value, and we will keep this Ta value constant. And let's say we take it to some, okay, 2.5 times compared to the previous one. So Ka was 10, here Ka is 2.5, sorry, 25. So what happened? Visual inspection says over here from the time domain simulation, we can clearly see that these oscillation are now, even after 30 seconds, well, it is reducing. It has a declining trend, but however, still declining trend, but even within 30 seconds, it hasn't settled down. So probably it would take much longer actually to settle down to some steady state values. Similar case, similar kind of response is observed for all the other three variables. Okay, even within 30 seconds, it's not settled, but it has a reduced, it has a tendency to get settled ultimately to the steady state values. Why? Because you can clearly see now. Now let's try to see the eigenvalues. What is happening with the eigenvalues? Where are the locations with respect to the previous case? So in the previous case, that is when AVR gain was 10, the location you see, the location of the poles or the eigenvalues was, okay, it was minus 0.2. So which one is the dominant eigenvalues? There is another term you might find in the literature, that is dominant eigenvalue. Dominant eigenvalue simply means if you compare the magnitudes of the real part, the one which is nearest to the imaginary axis. So among these three, the nearest one is minus 0.2, the complex one. So probably here, and then minus 1 is there. Minus 99 is far away, or somewhere there. So it is not a problem. So these are the dominant eigenvalues. They will actually decide, they will affect mostly the dynamics of your system. Okay, that's why these are known as the dominant eigenvalues. So it is in the range of minus 0.2, and the frequency is 6.844, not a big problem. But if we increase the gain, to 25, so it was minus 0.2. Now you see it is coming back. Actually, the value is now getting closer and closer to this y-axis. So this was minus 0.2 something. So if it is minus 0.046 means what? It is now moving actually towards the y-axis. So it is moving towards the y-axis, and it is pretty close. It is, you see, minus 0.0466. Whereas the other two, they have shifted to the other side. It was minus 1 point something. It is shifting there. It was minus 90 point something. It is shifting far towards the left. So these are not the problem. The problem is happening because of this till now, because these eigenvalues are shifting to the right towards the imaginary axis, and they have a tendency to go to the right of the y-axis, and that would be catastrophic in terms of stability. So, and the time domain response also suggests that, well, the oscillation magnitude, because of this shifting, these eigenvalues getting shifted towards the right, but still they are on the left. They haven't shifted totally to the right of the y-axis, but they are nearing, they are getting near to the danger zone. Okay, so you can see the magnitude is not getting dried up even after 30 seconds of simulation. But still we can call it, okay, this is stable, still stable, because all of the real part of the eigenvalues are negative. Still we are in the stable zone. Now, next, increase the Ka value a little further. Now K is 50. So you see that, okay. So this was let's take these two first. So this was 98. So probably it has shifted a little bit to 97, minus 97. This was -2. It is now -4. So it has now shifted a little bit more. But this one has now shifted to the right. And this is the problem. So you have a complex pair of eigenvalues whose real part is positive. The frequency has increased a little bit. It was in the range of 6 point something. Now it is 7.040. But it's not the main problem. The main problem is this real part having a positive value. So you see they have shifted to the right of the S plane. This is the sigma. And correspondingly, the time domain response also suggests that, well, the system is now unstable. So you see the low frequency, it is of, again, still the low frequency, 7.04 something divided by twice pi. So it is still in the 1 point something range, hertz, of course, in hertz. But the oscillation, you see, it is increasing. Del delta, you see, in 30 seconds, it has reached to, this is in degrees, of course. So how much is this? More than 20 degrees, okay, more than 20 degrees deviation. Synchronous speed, in the previous cases, it was coming back to the synchronous speed because del omega was becoming 0. Now you see del omega is rising up. So this is exponential instability case. Okay, there's a positive real part in the eigenvalue. So system response is catastrophic. So in conclusion, we can say, well, if we want a high gain in our excitation system, why would actually we expect high gain? Because high gain would help us in our helps in steady state or static stability, we should say. So high gain of the exciter, high gain of AVR actually helps in steady state response. But high gain of the exciter actually hampers the dynamic response, as we have seen. So first of all, why we need high gain? High gain is because this gain is actually the gain of the voltage regulator. And it amplifies actually the error that is being generated. So to get rid of the error as quickly as possible, so if you look at the error that is generated. So this with the gain we're talking about is this. It is located over here. This is the gain block. Okay. So you're talking about this. So this gain actually helps in enhancing this, whatever error you have here. Okay, del VT minus del VREF or del VREF minus del VT. So high gain over here actually helps in your steady state analysis or steady state response. But the high gain over here actually hampers the dynamic response. So we are actually in a dilemma. Okay, so what to do? We can't actually reduce the gain because in that case we will lose this benefit. But at the same time, we can't allow very high gain, okay, because in that case, the system is going into the unstable zone in terms of small disturbance stability or the low frequency oscillation problem. So what to do? We'll keep the gain high and we'll take help of some signal which we haven't yet considered. And that signal would come in the form of del Vs, and that would be taken from the output of the PSS, the power system stabilizer. So this is basically the history of the power system stabilizer, why it was introduced. Okay, so they are going for high gain operation, high gain exciter, fast exciter. But they found that, well, it creates, if we go for very high gain, it creates instability in the form of low frequency oscillation. So what they did, then they introduced the concept of power system stabilizer, which is actually some form of supplementary control signal. Okay, so this PSS, the power system stabilizer, would simply give us some additional signal which would be fed into this summing junction at this specific point at the input side of the fast acting voltage regulator. And we'll see how we are going to design it and how it is actually going to affect the LFO problem, how it is going to address the LFO problem, the low frequency oscillation problem. So for that, we have to specifically find out that how this EFD block is actually affecting the other part of the system. Okay, by other part of the system, I mean you can clearly see that with the introduction of this exciter block or this voltage regulator block or AVR block, we are increasing the Ka value, and that is actually affecting the stability of the system in the form of low frequency oscillation, specifically this set of eigenvalues over here. So the complex conjugate pairs are actually getting affected. Now, if you want to see specifically which state it belongs to, or this set of eigenvalue belong to, then you have to take help of participation factor analysis. And you can clearly, in that case, if you do that, then this, you will see that they are mostly related with these two states, delta and omega. This is related with EQ dash, and this is related to EFD. Probably I will talk about little bit about that participation factor later on in some of the classes, but not today. But using the participation factor matrix, you can easily identify that which of the state are actually participating in which of the eigenvalues. So because you see there are two eigenvalues, remember, plus and minus, and they belong to this combination, delta and omega. The third one here, you'll find that this is related to the EQ dash or delta EQ dash actually. So this is del delta and del omega, and this is delta EFD, the exciter eigenvalue or the exciter state. Okay. So that means when we are introducing this exciter block, we are increasing the gain of that block. That is actually hampering the states associated with del delta and del omega mostly. Why is it happening, or how this effect could be analyzed? So we will see how they are interlinked actually, how these values are interlinked. To find out that, we will now go to the topic of the Heffron-Phillips or Phillips-Heffron block diagram. So any question up to now? Because we'll move into the block diagram representation of this system now. Any question over here?
Sir,
Yes.
the PSS signal has sign positive. Why it is positive?
No,
negative?
PSS was not positive, I think. Okay, let me see. We haven't yet introduced PSS. This is just the block that I have shown. Okay, PSS could be positive, could be negative. We will see. We'll see. Don't worry. The main thing is that you will have some signal input into this summing junction. Okay. We haven't. Okay, I think, yeah. So here it is positive. Del VS is positive. So let's see. Let's see. Most probably I have kept it positive. But whatever you do, ultimately, you have to keep the sign same throughout your modeling. Okay. You can't say here it is positive, here it is negative. No. Okay. So you have to keep it. If it is positive here, if you assume it to be positive, then you have to keep it positive. So you're simply saying that I'm adding a signal. I'm adding a signal, or the deviation in the signal which is coming out from the PSS block. So this is addition. So yeah, it is positive over here. I've kept it positive. Okay. But we haven't yet discussed how to model this PSS. So we'll take it today, inshallah, if we get some time. At least I have a plan to start that topic. Okay, so let's stop. Any other question? Probably not. So now let's move on to there is that slide. Okay. Now let's move on to this. Okay, so now what we will do, we try to see the interaction in terms of block diagram. So simply the Phillips-Heffron model that would allow us to get the transfer function representation. So as you know that a simple dynamic system could be represented in different ways. Specifically, one of the ways we have considered till now, that is the state space model. Another way, which is familiar to you, probably the state space model wasn't familiar to all of you, but at least the transfer function model is familiar to all of you, should be. So the Phillips-Saffron model basically allows us to look at the system, that is the single machine infinite bus system, and that is the fourth order system. We would like to represent it in terms of the transfer function, and that would allow us to see the interlink, how actually this introduction of delta EFD, the exciter block, is affecting the del delta and del omega specifically. That is actually showing us the low frequency oscillation problem. So now let us see the transfer function representation of this block, and simply that transfer function representation was proposed by these two guys. So that's why the name goes after them. And later on, of course, this is the basic building block because we are only considering the single machine infinite bus system. Later on, the same model were used actually for extending the single machine infinite bus system to the multi-machine system. And in the same manner, if you add any additional device to your system, like any flexible AC transmission system or high voltage DC transmission system or anything like anything like that, then this Phillips-Saffron, you can take help of this Phillips-Saffron model. That is the basic building block, and you can extend it to include the remaining dynamics of the additional devices to the system. But simply again, this is nothing but the transfer function representation. So what we will do, we will take the state equations one by one, and we will try to get the corresponding transfer function, and ultimately we will combine all of them to reach at the Phillips-Saffron model. So let's start with the fourth order model. So again, we have all the same four equations, again in the linearized form, of course. So again, we will see the 6K constants and some system parameters present. We'll take one by one. So let's start from the first one, which is del delta dot equals omega base into del omega. So what we do simply, we know that this is in the time domain, because this is nothing but d del delta over dt. So this is simply d del delta over dt, and we all know that this in the Laplace domain would become s del delta, where s is nothing but the dy dt operator. So this is what is done. We have replaced del delta dot by s del delta, and on the right hand side we have no differentiation operator. So simply it is omega base into del omega. Then what as we know that in the transfer function representation, we have to relate the input and the output. So we are keeping del delta as the output and del omega as the input. So we get this block, omega base divided by s. So this is the omega base divided by s. This is the block, transfer function block between the del delta variable and del omega variable. Okay, very simple. Next, we take the second equation, which is the del omega dot equation. So this is the del omega dot equation. Once again, we are taking del omega dot as s del omega. So this is nothing but s del omega. Okay, if I come from here to here, and then I take this twice hs. So we're taking this to the other side. Then you see there is another minus d del omega. So I'm taking this as d del omega. And then I'm writing minus k1 del delta minus k2 del q prime plus del pm. And then I'm taking this common 2hs plus capital D into del omega equal to whatever we have. So this is what. So this is this line. And then I'm taking a transfer function representation between this del omega, which is now the output, divided by whatever I have here, minus k1 del delta minus d del omega minus k2 del eq prime plus del pm. Okay, So, oh, I've done a mistake probably. Yeah, so this shouldn't be here. This is already taken to the other side. So I have to correct it. Okay, I will take it later on because this has come as an image. So this will not be here because this has already been taken to the other side. Okay, so there's a mistake. So you have to correct it. Okay, so we have del omega divided by minus k1 del delta minus k2 del eq prime plus del pm. So you have a summing junction here with three elements or three components. One component is minus k1 del delta. So you see this block was already drawn in the previous slide, which was the relation between del delta and del omega. Del omega was the input in that case, and the block was omega base over S. Now, this del delta is required because you have to form minus k1 del delta. So the del delta is fed back with the gain k1, then with a minus sign over here. So at the summing junction, you will have a minus sign, that is minus k1 del delta minus. So this is k1 del delta with the minus sign. So that is your k1 del delta. Then you need minus k2 del eq prime. So we don't know yet from where we would get del eq prime. So we are just keeping it as we know that del eq prime would be available. So once we get del eq prime, we would multiply it with k2, and this here we will get k2 del eq prime. And we have a minus sign because this is the minus sign. Plus delta pm. So the third input to the summing junction is plus delta pm. So this is where you have, this is the input to the overall system, overall block over here. And the transfer function is 1 upon twice hs plus d. So this is the transfer function. So this is how you do it. Then we take the third equation, that is del eq prime dot. So the del eq prime dot equation, the third state equation from the fourth order model. So you see there is del eq dash equals 1 upon tdo prime, tdo dash multiplied by delta efd minus k3 del eq dash minus k4 del delta. Again, what we do simply, we take this s multiplied by del eq dash, then tdo dash is taken. So make it tdo dash. Then we have another k3 del eq dash. So plus k3 del eq dash. So it would be equal to delta efd minus k4 del delta. So again, you can take del eq dash common. So you will be left with s tdo dash plus k3, whatever you have here on the right hand side, and then you can come. So this is the same thing over here. Okay. So then you simply take this as the input from the summing junction. This would be formed with the help of the summing junction over here. So you have a plus input to the summing junction, which is delta EFD. So we will take this delta EFD in the inshallah the next slide from where it's coming. But for the time being, we'll take it as available to us. So delta EFD is one input to the summing junction minus K4 del delta, and this is coming actually from the other part of the blocks. Okay. So this is coming from the block where you have, this is omega base by S, and this is your del omega. So we have already shown how it is formed. So this is coming from there. So once you have del delta available, you multiply it by K4. So this is your K4 del delta here. And then you have the minus sign. So it is minus K4 del delta plus delta EFD. So this is your transfer function block K3 plus S. Again, this is STDO prime, all the same. D is missing. So probably this also requires some correction. This is STDO prime. And the output is this one, delta EQ dash. Okay. So this is how it is obtained. Now the thing that is left is simply this delta EFD from where we are getting it. So this del EQ prime, you see it is getting available here. It is available now. So this would be actually taken. In the previous slide, we said we'll take it we'll get it. So this is delta EQ dash. It is getting into the block of K2 gain block. So this delta EQ dash would be obtained from here, from this block. Okay. So this delta EQ dash would be going to that K2 block here. And ultimately they would form a closed system. Okay. We'll combine all of them finally. So the last equation, the fourth equation, let's take it. The fourth equation is about the delta EFD dot. So this is K over TA, it's the EFD in the time domain. So delta EFD dot K over TA, del V ref minus K5 del delta minus K6 del EQ dash. What I have done, I have simply ignored here. If you want, you can assume the presence of plus del VS, that is the PSS input. But actually we have not included PSS yet. If you want to include it, then simply you have to add another input to the summing junction that is in the form of delta VS. Okay, nothing special. For the time being, we are assuming delta VS is 0 because there is no PSS. So we are not writing it explicitly. So we have del Vref minus K5 del delta minus K6 del EQ prime minus 1 upon TA delta EFD. If we simplify it again by taking it as S into delta EFD, you have some EFD delta EFD on this side. So you bring them together on one side, and this is left on the right hand side. This is what you are left with. So then you take delta EFD as the output, this whole thing as the input to the transfer function block. So you are left with the exciter block. So this is nothing but your AVR transfer function. So this is your AVR transfer function, which will give you the delta EFD as the output. And these things are the input. So del EQ prime multiplied by K6. This is this block. K5 del delta, this is already here. So at the top, you are getting K5 del delta with a minus input. At the bottom, you are getting K6 del EQ dash with a minus input. And the third input to the summing junction is del Vref. So then you have this AVR, Ka over 1 plus STA. And the last one over here is the output here is delta EFD. So this delta EFD would be ultimately going into the previous block, as I said. So this delta EFD is actually coming from this block over here. Okay, so we have got all the 4 state variables as the output of transfer function blocks. Now we would be combining all of them. So when we combine all of them, so till now we have got the building blocks for the Heffron-Phillips model or Phillips-Heffron model. Now we will combine them and we'll get the complete picture as a single block. And remember, we have 2 inputs. One input is del Vref in the exciter block. Another input is delta PM in the del omega block. Okay, the second state equation. So when we combine them, we get this equation, this whole picture together. So if I want to separate them again, so if I want to highlight them, what we did. So this is the first one. Okay, del omega and del delta, these are related in the first one. In the second one, what we did, we took K1 del delta and we took K2 del EQ prime. So these are the 2 inputs. And this one is the second one. Actually, this one, K1 del delta. So this one minus, plus del PM. So this is the second one. Okay. So this is the second one. So now they are combined. The third one is del EQ prime. So we had this delta EFD and we had K4 del delta. So K4 del delta came as a minus and delta EFD came as the plus. So this is the third block. And the fourth block is the remaining one. So it is the K5 okay, so K5 del delta as the minus, K6 del EQ dash as the minus, del VDEF as the input. So these are the four blocks separately identified here, and then we combine them. So simply after combining, you get the complete block. So now what is done actually, we have further separated these two building blocks or this whole block into two sub blocks. So you see the top block is known as the mechanical loop and the bottom one is known as the electrical loop. Why? You can clearly see that the terms that are coming out, or the variables that are coming out as the output in the upper green block or green dotted block, that is called as the mechanical loop. You see these are nothing but the mechanical quantities, the angular speed of the machine or angular position of the machine. So these are mechanical quantities, okay, mechanical quantities. So these are the mechanical loop. This is why it is called as the mechanical loop. And the lower one, the blue dotted block, we call it the electrical loop because you see it is the exciter output voltage and the QX is internal transient voltage. So these are voltage terms. Both are voltage. So they belong to electrical loop. And the top one, del omega and del delta, these are angular speed and angular position. They are more or less related with the mechanical motion of the system. So they are treated as the variables in the mechanical loop. And this is the interaction. You see how they are interacted. So this is the interaction. You see this EQ dash is actually having some effect from delta EFD because it is a fourth order system. So EQ dash is a function of delta EFD. EQ dash is a function of delta EFD. Delta EFD again is a function of this block. So if you change K here, the gain of the exciter here, it would actually transmit through this block, through K2 block to this mechanical loop. So this is how this interaction, this K value, we are changing it, increasing it, and thus it is actually affecting both del omega and del delta. So this is the important path for signal transmission from the exciter gain to the mechanical loop. That is the combination of delta and omega, or del delta and del omega. And this is how actually some damping torque is provided from this delta EFD, or from with the help of Ka, the delta EFD is providing some signal into the mechanical loop, and we call it as in the form of the damping torque. And in this case, we can clearly see that if we change Ka, this damping torque slowly, it was initially when Ka was, initially it was how much? It was probably 10. Damping torque was still positive. So if we call it as TD, it was positive. TD from exciter, it was positive. When we made it 25, TD was positive still, but a reduced value. Okay, started to reduce. When we made it 50, TD became negative. So it reduced further and now it became negative. So if you increase Ka, your damping effect provided by the del EFD block is getting negative. So this is how you can conclude that the EFD is providing some signal in the form of torque. Why we are calling it torque? Okay, why we are calling it torque? Remember, the input to this system, what are the inputs? What is this? This is mechanical input power. In per unit, power is the same as torque. So we can also call it delta Tm. Okay, K1 del delta. This is another form of torque. We call it synchronizing torque. And this D, the effect of D is actually giving you some sort of damping torque. So anything else that would come and reach at this summing junction and will be added up ultimately will be some other form of torque. And that's why we are calling this contribution from this EFD through this EQ dash loop is another form of torque. Okay, so this is why we are calling it damping torque. Why damping torque? Because it is actually hampering the damping of the system. Okay, so previously when Ka was 10, we start with Ka was 10, your system response was stable. It was stable. When K became 25, the stable scenario, it was still stable, but the scenario was something like that. The decay was pretty slow. Okay, the decay was pretty slow. And we saw that even after 30 seconds, there was oscillation, but it was decaying at a slow rate. But when it was 50, you see the damping became negative. So it was opposite. So it was rising with respect to time. So that is negative damping. Whereas without this Ka block, there was no such problem. Without this Ka block or without the exciter block, whenever we dealt with the third order system, we actually didn't have Ka. Okay, we actually didn't have Ka. So this block was not there for the third order system. So we didn't have to bother about the exciter gain in that case. But when it became the fourth order model, we see that this is the problem happening. So in conclusion, we will say that, so this is the problem identified with the large exciter gain. On one hand, we need the large exciter gain for a steady state, good steady state response. But for dynamic response, the system is having problem for large gain. So what we will do next, we will try to design the power system stabilizer and try to mitigate this LFO or low frequency oscillation problem. So we are not going to reduce this Ka. This could be one solution to reduce the Ka, but that would actually take away some of the other benefits that we would have for the system. So we'd keep the same gain value, K, let's say at 50, which made the this system unstable. And we would be, remember this summing junction, we would be actually adding up some del UPSS, which is actually the same as del VS. So now in the next class, inshallah, we will be designing, we'll be seeing how, we will see how we are going to design this del UPSS or the PSS block. And in practice, actually, there are many methods to design this PSS, but we'll take one actually very initial method just for the understanding of the PSS. So the method that we will take is known as the phase compensation method. But as I said, there are many other more recent methods. You can apply many other techniques just to design this PSS. But the one that we will use is the phase compensation method. Okay. So there's not much time left. So probably I will start it in the next class, inshallah, on Monday. Okay. Any question? No question. Okay, so in that case, let me conclude today's session. And I will post an assignment, just the simulation results that I have shown today. Simply you have to reproduce it. Okay. I have shown in the previous slide actually that I'm changing the Ka value, and you have to get the responses of the eigenvalues. Okay, so that's the fourth order system. So you have to simulate the fourth order system as your second assignment. I will post the detail in the Google Classroom, inshallah. So you have a fourth order system. You increase the Ka value from low value, and you check the eigenvalues, and you simulate the time domain responses. Okay, and see whether when it is getting unstable, whether the eigenvalues are supporting your time domain simulation results or not, and all these things. So this would be your second assignment, inshallah. Okay, so see you inshallah on Monday, because we have we are not going to continue on Wednesdays. So those Wednesday classes are shifted to Mondays around same time, maybe 7:15, inshallah. Okay, see you then. Assalamu alaikum.
Assalamu alaikum.